Excellencies, distinguished guests, ladies and gentlemen, we are now continuing our meeting to the next program. That is to hear the first keynote speech, which will be delivered by Professor Hiroyuki Iida from Japan Advanced Institute of Science and Technology in Japan. The keynote speech will be moderated by Mrs. Anggina Primanita. Please welcome Professor Hiroyuki Iida and Mrs. Anggina Primanita.
Okay, thank you very much. The Honorable Rector of Universitas Sriwijaya, Professor Anissa Gauf, the Honorable Chairman of our IEEE Indonesian Section, Dr. Wahyudi Hasbi, the Honorable Dean of Faculty of Computer Science, Mr. Jaidan Jauhari, keynote speakers, distinguished guests, conference chairs and participants. Assalamualaikum warahmatullahi wabarakatuh, and a very good morning. My name is Anggina Primanita, and I will be your moderator for this keynote section. First of all, let me remind you of our agenda for today. So these keynote sections will be divided into two sections, which is the keynote speech by Professor Hiroyuki Iida, and the speech will be around 30 to 35 minutes long. Following that will be a Q&A session, which will run for 10 to 10 minutes long. And for the question and answer, we are accepting your question through the Zoom chat feature. So if there is any question, do not hesitate to ask away in the chat. I will curate your question at the end of the speech. Before we start the keynote speech, please let me read a very abridged version of Professor Hiroyuki Iida's curriculum vitae. So Professor Hiroyuki Iida received his PhD degree in heuristic theories of game research from the Tokyo University of Agriculture and Technology, Tokyo, in 1994. He is currently a Japanese computer scientist and a computer games researcher with focus on game refinement theory, opponent model search, and computer shogi. He is currently the trustee and the vice president of Educational and Student Affairs with the Japan Advanced Institute of Science and Technology, JAIST, the director of the Global Communication Center and the Research Center for Entertainment Science, and also the head of the Iida Laboratory in JAIST. His research interests include artificial intelligence, game informatics, game theory, mathematical model, search algorithm, game refinement theory, game research, and entertainment science. And currently, he is a member of the board of the ICGA as a secretary-treasurer and a section editor of ICGA Journal. So that is Professor Hiroyuki Iida's curriculum vitae. Now, Professor Iida, if you are ready, then the floor is yours.
Okay. Thank you, Mrs. Anggina. Mrs. Chairperson, can you hear me? My voice is okay?
Yes, we can hear you very clear.
Okay. So good morning, everybody, and greetings from JAIST, Japan. Perhaps you enjoyed a kind of summer there. Here it is winter season, still with some snow. Thank you for this opportunity, inviting me to giving the talk. It is my most pleasure to be the part of the conference ICONICSE 2021. Congratulations on wonderful organization of this conference. Well, for the last few years, I took my pleasure to host a PhD candidate from UNSRI, Mrs. Anggina, actually chairperson of this session. She has been what is my slide? Hi, Mrs. Anggina.
Yes, sir. I think you need to share screen of your slide.
Yeah, I asked the first page. Yeah, first page.
The first page. Okay.
Yeah. First page, please.
Okay.
This is first page. Fantastic. Okay. So, PhD candidate from UNSRI, yes, Mrs. Anggina has been investigating way Bridging AI, artificial intelligence, and entertainment. Recently, she has completed her PhD dissertation entitled Computing Games and its Implication to Measuring Playing Experience. She successfully found a way bridging AI and human mind using the games as testbed. Her work is one of the pioneering great contributions to open a new research area, which we call it entertainment science. Therefore, I'd like to share some aspect of entertainment science today with a focus on motion in mind theory. That is a bridge between physics and play. Yes, next slide, please. Yes, well, let me share some of the Dr. Angina's PhD work by showing this slide. Yes. I would say, no. Previous slide, previous slide. Too much. It's previous slide. Yeah, Dr. Angina's slide. Yeah, this is very important. Yes. So, how I say, my slide is not so well. I can't see it. Something wrong. Okay. Over history, games have been served multiple purposes. It serves as a fun activity for players who need entertainment to become testbed for AI. Solving game is beneficial in providing a better understanding how information is processed throughout the game. Uncertainty in games affect the way a game is solved and the way the game is experienced. Previous work have interpreted uncertainty in game progress through various means, but there have been no clear links among those interpretations. In this study, the probability-based proof number, PPM, and single conspiracy number, SCM, were used as domain-independent indicators to analyze how uncertainty affects the various game elements. The PPM search exploited information from certain and uncertain information to reach convergence in solving games. Meanwhile, SCM evaluates game states difficulty and describes game playing patterns to understand play positions better. Experiment result in her PhD work demonstrate the link between the search indicator and the measure of entertainment, where uncertainty plays a vital role in both contexts, verified from both two-person and single-agent game. Such a situation is also crucial for both computation and entertainment measures, since it impacts both quality of information and expected game playing experience. So it's my pleasure to introduce and share what she has done in her PhD project. Anyway, congratulations. So next slide, please. So already a chairperson introduced what I am. Yeah, actually I had two stages in my life. My first stage was a Japanese chess shogi grandmaster when I was young, but I quit my career just before the 30. When I was 30, I changed my mind to be a kind of a researcher. Yes. Next slide, please. Yeah, right. I enjoyed my PhD work, some say 30 years ago. Professor Yafan Hirik was my supervisor, who has been a super expert in the domain of AI, especially with computer games. Around early 1950s, maybe you know, both Claude E. Shannon and Alan Turing independently proposed an idea of main framework of games research based on minimax concept. Actually, Dr. John von Neumann proposed the minimax equivalent concept in his 1928 paper of game theory. The half-century passed since the time of Claude Shannon and Alan Turing. Computer chess won against human grandmasters which follows the look-ahead search with the minimax-based algorithm proposed by both of them. In the history of computer chess, many ideas, new ideas, such as efficient search algorithm and hardware technique like a parallel computation came out as great contributions for development of computer science in general. My PhD topic was opponent model search or OM search. Actually, the previous slide, please. Previous slide still. Yeah? Yes, yes. In the minimax-based game tree search, it is always assumed the opponent player will minimize your profit. However, this is not true in the actual game situation. Once we have some knowledge about opponent, we might gain some advantage by anticipating opponent, for example, weak point, then expect to result in a better performance than minimax sense. This idea has been applied in various contexts, such as tutorial purpose, etc. Yeah. Then anyway, I've been working for the last, say, 30 years for this topic entitled Using Games as Experiment Testbed for AI Research. So now, next slide, please. Yes. So in the domain of computer games, artificial intelligence AI has met a singularity. For example, Deep Blue won against Garry Kasparov, chess world champion, in 1997. The computer shogi Tacos played with Grandmaster in 2005. And AlphaGo recently won against Go Grandmasters. Then AI became more than singularity, which I call it disruptive AI. This is because AI can see an almost perfect solution or solving games. We are somehow enforced to change the rules. The game change. AI is something like a monster to destroy the game. Because we know the theoretical value of the game, almost no interest to play. But that's why we call it disruptive AI. So now is the time, therefore, to consider a new research paradigm. The previous paradigm was, say, program a computer to win against a human champion. The recent paradigm was a program a computer to run by itself and eventually win against a human, any human. But I propose here, a new paradigm is program a computer to enjoy together with human players. The meaning, computer understanding, entertainment aspect when playing the game together with human. Next slide, please. So here are three guys from history who mentioned something about games and importance to using the game as testbed for research context. For example, Leonardo da Vinci says something like, simplicity is the ultimate sophistication. It's an important concept in designing game. Next one is, how I say, next slide. Next guy, from history, how I say, Leibniz, pronunciation. He said, human beings are never more ingenious than in the invention of games. It's so difficult to design very, rational, appropriate game rules. For example, Albert Einstein also mentioned play is the highest form of research. As you know, game has been somehow good testbed for the research context. Next slide, please. Next slide, please. Okay, thank you. To start up a new paradigm, recently I took my pleasure to introduce a new concept. I call it motion in mind. Here is my first publication in this direction, using games to study law of motion in mind. Let me share a little bit from this abstract, establishing several physics quantities such as mass, speed, and acceleration relative to the game progress model allowed for the player's entertainment experiences for the specific game to be determined through a Newtonian laws of motion, especially the force, momentum, and the potential energy. Such a law of motion reveals the feeling of player in their mind, mapping different games originated from different cultures to the state of the human mind, a measure of sophistication that leads to a natural yet pleasurable experience. Uncovering the fundamental mechanism of gameplay mechanism that have been the primary goal in our laboratory. Game refinement theory is the fruit of labor for several years. The relationship between game progress and entertainment experience from the perspective of the game design. Several sub-branches of the study have been explored through board game, sports, and video games. From a non-game context had also been previously explored, business, education, loyalty program, etc. Interestingly, all of those studies found the game refined measures coverage that's approximately similar zone value, a region named as novel uncertainty. Next slide, please. Here is a corresponding table between physics and gameplay in our current approach. In the table, the physics, the gameplay, Y, displacement, in game context, solved uncertainty, the T, a time and length, the V, velocity, and in game context, win or score rate. It's a kind of the rate of solving uncertainty. M, the mass and difficulty rate in game context. A, gravitational acceleration in physics, but in game context, informational acceleration. Momentum P, momentum of game in game context. The U, here the gravitational potential energy is in a free fall motion. In the game context, the potential energy in game is represented by, say, EP. Yes? It's an analogy of the motion, dimension of challenges using the mass. The basic assumption is a zero-sum game state, M plus V equal 1. In both games, actually, we approximate velocity V equal B over 2D. The B stands for branching factor of game, and D stands for the length of the game. In scoring game like sports, the V is approximated by a G over T. G stands for the game score, and the T stands for the total shoot attempt. This is our how I say, analogy from the physics. Next slide, please. This is the second paper in this direction, which focused mainly on the information acceleration or gravity of play. Yes, maybe I will skip, and later I will explain a little bit more detail. Yes, so therefore, next slide, please. In this talk, let me focus on three aspects, which I call it a principle. Yes, here the first, principle one. People would feel entertaining or sense of thrill when the outcome of the event, like game outcome, is uncertain until the very end. Actually, you might agree with me, because if we know the outcome of the game on the way, before the end of the game, that's be the boring. Yes? Therefore, this principle might be reasonable. Next slide, please. Actually, this is a follow-up of the principle one, gravity of play, quantifying what we enjoy about game. Let me explain from this a slide. One key measure in the model of motion in mind is an acceleration of gravity in mind. In analogy with Earth's gravitational acceleration, in sufficiently defined games, the model establishes a relationship between the effort that player has to make to advance and the degree of challenge a game represents. The gravity was calculated associated with a wide variety of games that evolved through history, including classical board games like Chinese Go, chess, and shogi, the popular sports like soccer, tennis, and basketball, and the video games such as fighting games and strategy game. Actually, in this slide, on the right side, we could see the dimension of the century, almost 4,000 years, the game of Go started with some degree of the acceleration, like a go 9 by 9, then transform to a 19 by 90 to like after say more than 1,000 years with some degree of the acceleration. Then on the right side, you could see the chess history starting like a 4th or 5th century, yes, a Chaturanga to a modern chess variation after more than 1,000 years, and with the same degree of the acceleration with Go 9 by 9. This is a rough overview of the history of Go, traditional board games, Go and chess. This is a kind of symmetric. That's kind of an interesting point. It's gravity of the play. Yes. Next slide, please. So momentum. In physics, various physical formulations have been established around the motion of an object. The most fundamental of such formulation was the measure of the force, momentum, and the potential energy. In this study, establishing those formulas in the game involves analogical rings that were based on the game progress model. The table in the, a previous slide shown the analogical connection between the physics model and the game progress model. Here, a momentum depends upon the variables mass m and velocity v. The momentum of object is equal to the mass of the object times the velocity of the object, namely a momentum p equal m times v. The equation illustrates the momentum is directly proportional to object mass and directly proportional to its velocity. A notion of momentum in game plane is defined with a focus on two factors: hardness to move in the game, mass m, and game progress ratio, velocity v. A game's energy is defined as amount of required game information a player needs in the game progress. It explains the expectation of player in finishing the game. In the game progress, the game's energy reflects the amount of anticipation the game may give to the player. Concerning the potential energy of gravity, the game itself will be attractive to players like gravity in physics. And the potential energy of this attraction is the energy of the game. So next slide, please. Yes, here the principle 2, a momentum conservation. Potential energy, EP, is assumed to be conserved over time and transformed into momentum of game's motion, say P1, and motion of mind's motion, P2, namely EP equal P1 plus P2. Hence, it is expected for P2 to be a reliable measurement of engagement. So next slide, please. In the special relativity, yes, energy and momentum are hyperbolic. Both momentum and mass can be considered as a main manifestation of energy. Under certain circumstances, the mass of the substance can be derived from energy of interactions between substances. And the mass of other substances can also provide the energy of substance. Hence, energy, momentum, and mass should be considered as a form. In this study, the potential energy is assumed to be conserved over time and transformed into the momentum of game's motion and the momentum of mind's motion, from which a new measurement of engagement is proposed. Analogous to the law of conservation of energy in classical physics, EP is expected to be conserved, where the momentum of game playing motions in the game contains both objective in game and subjective recognition in mind, albeit are different in levels. So next slide, please. Here is a law of conservation. Yes, the momentum conservation, energy conservation, the momentum conservation, game's motion P1, mind's motion P2. And game's motion represent the change of score or change of moves. The mind's motion represent the change of winning prediction. Then energy conservation, EP, stands for game's motivational potential. It's like the amount of the information perceived. The EQ is the mind's motivational potential, amount of information expected. Actually, a objective and subjective, respectively. Next slide, please. Here we showed some conjectures, 1 to 4. Conjecture 1 is a momentum conservation. Actually, a subjective momentum P2, a momentum's mind, is a reliable measurement of engagement. Conjecture 2, it's like a high competitive excitement is a peak of the P2 momentum, the plus case and the minus case. The conjecture 3, energy conservation, EP, game's energy, and EQ, mind's energy, is a reliable measurement of motivational potential. Conjecture 4, natural equilibrium, play experiences in a constant state of seesaw game, implying the greatest attractiveness, something like that. So next slide, please. So psychology and comforting mind, considering the objective momentum P1 and subjective momentum P2 from a gambling perspective, for example, then V1 and V2 are the win rate or the velocity for the objective and subjective motions, respectively, being a function of mass M. Here is a kind of a remark that objective motion denoted by P1 is an motion with constant acceleration, which relates to the sense of thrilling, excitement, while the subjective motion denoted by P2 is a motion with constant jerk, the change of acceleration, which relates to the sense of thrill and engagement. A conjecture 5, addictive event postulate condition here, Vt equal or more than 0.5, and the mass equal or less than 3 minus root square 5 over 4. It's like a peak value of the momentum 2. The subjective win rate V2 is aligned with a prospective theory, well-known theory from the economics, which defines the utility of losses that was distorted and regarded as higher utility compared to gains of equivalent value, known as loss chasing by gamblers. In the context of motion in mind, M equal or higher than 0.5 implies a greater emphasis on losing, where the minimum win rate in mind should be offset by about 12% in the range of 0 to minus 0.125. Thus relates with high tension event. Meanwhile, M less than 0.5 corresponds to the win rate that's considered as standard in mind, the V2 in 0 to 1 range. Thus relate to the high expectant event. This condition is more prominent when V2 equal or higher than 0.5, meaning M equal less than 0.919. This situation demonstrates the acceptable comfort people willing to accept in mind when facing risk or adverse loss. Next slide, please. How long should I still have it? Maybe almost done. So force in mind and perception. Yes. Force in mind indicate the player's ability to move in game or relative to player strengths in general. This situation was due to the relationship between large candidate options directly proportional to the magnitude of force retained over time, observed from the game progression. In other words, games with a higher number of options require attainment of force, thus associated with ability to play. Based on the acceleration of subjective motion, A2, acceleration 2, the game's subjective force can be determined. Obtained as the lowest point of F2, it's a negative peak in the graph left side. Such a peak implies the game pushes the player to acquire necessary ability, knowledge, instead of requiring the player's ability to move the game, F1, making it a good condition for the novice or educational purpose. Next slide, please. Yes. Now that we come to here, the principle 3. The difference between objectivity and subjectivity equals the total energy E. So namely, E equal to V1 minus V2. Yes. Next slide, please. Hence, it is expected the larger difference is a higher attractiveness of the game under the consideration. So here, slide shows a process dynamics and gamification. Actually, in the previous discussion, we assumed the mass is like average value for each game. Actually, in one game, we should consider such mass dynamics or velocity dynamics during the game. So therefore, process dynamics and gamifications is somehow important to analyze in a practical case. A general activity is depicted like a linear process or displacement. In this case, V is constant. And the gamified experience is when the delta V occurred, is meaning acceleration is constant. The dynamic change in the gamified experience are when there is an interplay of delta V and delta A, existence of the curve. That is an important case. So next slide, please.
Professor, sorry to remind you, we only have 5 minutes left.
Okay, 5 minutes.
Schedule.
Okay, I'm going to the.
I'm very sorry.
5 minutes. Okay, here is a summary, overall depiction of all types of games. No. Previous one, a graph. Yeah, right. In this study is given this figure. Based on the figure, it was found addictive event was suited on large, the P2 at M less than 0.5 and smaller P2 at M equal higher 0.5. Namely, the larger difference between EP and P1 momentum, the greater the engagement becomes. It implies a large difference makes people addictive in two directions. One is profit winning, the public gambling, and risk taken, popular sports like soccer events. Such a condition satisfies conjecture 1 and conjecture 2. Besides, the popular public gambling games such as pachinko and online casino was found to be located at M equal or less than 0.19, left side of this graph, which indicates the game was perceived to be fair in the gambler's mind, subjective equality, satisfying conjecture 5, and possesses enough games inheritable force to be played by both novice and experienced players, thus encourage continuity and prolong the play, satisfying conjecture 6. So next slide, please. Yes, this is a summary of motion in mind. In summary, various motion in mind measures with its related events were given in this table. The mass value point from the 0.19 to 0.78 in the graph from the left side to the right side. For example, M equal 0.19 is indication V2 equal to 0.5, so meaning subjective velocity, subjective rate of solving uncertainty. In this case, related event, comfort in loss aversion. So this means many people or some people might have engaged to join the addictive, how I say, like a gambling activity. Yes, something like that. And M equal 0.79 in the bottom of the table is like a peak of the P2 momentum, subjective momentum. In this case, related event is high tension excitement like sports, soccer, etc. So maybe I finish in a few minutes. Next slide, please. Yes, this is a kind of the future work from this study, motion in mind. If we try pushing the boundary of this research, entertainment, science, new research area, maybe there are some possibility to extend for each direction, like meta learning, music theory, behavioral science, psychology, education, data-driven design, knowledge discovery, business, and brain science, etc. Yes, why not come into this area? We welcome you to work together in this area. Next slide, please. Yeah, now I come again this slide. Actually, it's very much a congratulations, Dr. Anginer. successfully find a way bridging AI and human mind using the game as test bed. Yes. And also we are working together to open this area, research areas, like entertainment science. Yeah. This is my talk. Yeah. Thank you. Maybe next slide. We could enjoy the discussion. If you have any question, it's my pleasure. Thank you for listening.
Thank you very much, Professor Iida. Here we have several questions from the chat. So I will read the first one, which is from Mr. Dani Saputra. He wants to ask that a few AI games have beaten the professional, and the AI usually designed to win the game. So when the AI is losing, it's because of software and hardware limitation. So maybe his question would be, why is there only so few AI games that have beat the professional?
Thank you for the question. Interesting question. Actually, my recognition is different. Almost all games now AI is stronger than human. It just depends on the limitation of the computational resource. In this sense, you are right. Actually, how computer can become so stronger? So this means a deep learning idea. So this means with a larger computational resource, the computer can be trained, for example, 1 month, 2 months, or sometimes more. Of course, you have a rich resource of the computation. It makes it shorter, like 1 day or within an hour or within a moment. Yes, computer can become quickly more than human. This is a situation. For example, not only board game, chess, Japanese chess, Go, but also Dota 2 or some other incomplete information game like a poker, a bridge, etc. already far stronger than human player, almost perfect. This is a situation because of the machine learning technique, so quick advancement. Is it an answer to this question?
Yeah, I think that will be answering the question. We have the second question right now from Mr. Yopi Sasaki. So he asks about how to get public data research for game refinement theory. And also the second question is that what is the challenge of the game refinement theory development in the future? So is it still limited to only offering a measure, or there can be other challenges?
Thank you for this question. This is a very nice question. For example, first the question about the data. Yes, two ways. Actually, we collected the data in the two ways. For example, when we collect the data from the human expert players, like a chess, Go, etc., in that case, a human player, strong human player, usually resign when they notice the result of the game, even before the very end of the game. So therefore, game length should be a little bit shorter than computer case, because in the computer may not understand when to interrupt, when to resign. So therefore, one is data from human player. Another one is data from simulation with human, AI, artificial intelligence, like a self-play experiment. So therefore, we must be careful when we collect such data. So therefore, we carefully treat such data to compare together. Yes. The second one is a very nice question, encouraged into me. What is a challenging emotion in mind or game refinement theory? Yes. Essential idea is to understand what is the uncertainty in the target domain. Then, once we know a clear definition of uncertainty in the target game, we can define the velocity, meaning the rate of solving uncertainty. Otherwise, hard to define, appropriate or reasonable or definition velocity or mass. So therefore, when I involve this study, always I must be very careful to define uncertainty and define the velocity or mass, such a physics value. Yes. This is most challenging so far. But in the long term, challenging would be application to another domain I mentioned in the end of the slide. Yes, like pushing the boundary to other area, like a social problem issue. How we can apply this discussion, this study to other cases, for example, economic field or social problem, like a SDH program, etc. Now we are actually doing in this direction. Yes, I hope this answered currently to this discussion. Maybe not so fully answered, but is currently what we are doing in this direction. Thank you for this question.
Thank you, Prof.
Thank you very much. I think we already get the reply from Mr. Yopi Sasaki himself. Thank you. And then we have another question. I need to kind of translate, so it will take a little. So is there any impact from the difference of geographical location, geographical locations of the player to the entertainment science paradigm that you have set? Also, is there any subjective factor that is represented in this case, like in the factor of geographical difference? This question is from Mr. Ahmad, actually, yes.
Thank you for the question. Maybe I didn't fully understand the question, but I may try to answer this question. The point of this talk is the entertainment or potential attractiveness of the game or event in the target is, it depends and highly depends on the difference between subjective and objective. Yes. If such difference is larger, we could feel stronger impact or stronger attractiveness, engaged. If the difference is smaller, difference between subjectivity and objective is smaller, it's somehow boring because it's naturally, realized. So how it's related to the geographical, point? But I'm not sure how to answer this question. Dr. Anggina, do you have any idea?
Maybe I can rephrase my question.
Yes, please.
I have a thought that we can identify the subjective measure from the geographical location of the player. So do you think we can do that, or you think that subjective measure is already include the geographical difference for the player? So for example, a player from Indonesia maybe is different from the player from the Japan in regarding the subjective measure.
Let me show you an example. What is a subjectivity and objectivity in game context?
Okay, maybe the player from Indonesia more.
The result of the game.
Yes.
You see?
Yes.
Objective is a result of the game in reality. Yes. Subjective is a predicted result of the game.
Okay.
Prediction of the result before the game or during the game.
Okay.
If the difference between objective and subjective is smaller, it's boring because just as expected. Yes. But if the difference is higher, is uncertainty a lot, unexpectedness. Yes? That's an engagement, fundamental aspect of engagement.
Okay, so did you research about the subjective measure of the player?
I see.
Yep.
So player's issue.
Yes.
So far now, our discussion is more like a general, like game subjective games outcome.
Yep. Okay.
Not concerned about the players.
Not about the players. Okay, thank you.
That's maybe the next step.
Okay, sure.
Maybe more complex, I believe. more like a psychological issue.
Yes,
In
of
this
course.
case, the point is how we define the subjectivity and objectivity in the target.
Okay. Okay, because I see in your last slide
It's
you.
more like a subjective.
Okay. Okay, thank you very much.
You're welcome, welcome. It's a good question. Thank you.
Thank you very much. And this is the last question because we are limited by time. It's from Professor Siti Nurmaini. She asks, computers can do a great deal, but their nature are limited to algorithms. Whereas game is creativity. How do you define the gap between them? So like a computer is limited to algorithms, is limited to the makers, whereas game is pretty much creativity. So how do you define the gap between those?
That's a good question. Thank you. Thank you. Actually, I mentioned in the one slide, 3 guys from the history. One of the guys, Dr. Leibniz, already more than 200 years ago, 300 years ago, he mentioned the game design really genius ever in history. This means a design of the game is highly related to the physics, very reasonable and also related to the physics law. So this means a game design is very creative sense, and also game playing is also a creative sense. But such a emotional or human matter still can be established in a physics way. This is our approach. I hope this will be some kind of a hint or the answer to the question at this moment.
I think it's a very interesting approach to see whether the gap will will diminish and become singularity, as you mentioned before. So I'm very sorry, but we are very limited by our time here.
I'm happy to have a wonderful question. Thank you very much.
Yes.
Thank you very much, Prof, for your question, for your answer.
Is there anything, another closing remarks from Professor Iida before we close this session?
Yeah, actually, my real congratulations is wonderful organization of the conference and also fantastic discussion. I really enjoyed it. I'm so happy to be here. I wish you much success continuous in this conference. Thank you once more. Thank you.
Okay, thank you very much. Please a round of applause for Professor Hiroyuki Iida.
Thank you.
And with that, I'm closing this keynote speech and I'm giving it back to the MCs. Thank you very much.
Thank you, Professor Hiroyuki Iida, for the keynote speech.